Okay, so now we'll look at some of the applications of Laplace transforms. One very useful function which is used in this context is called as the Heaviside unit step function. This Heaviside unit step function is written as u, and it is defined in this way: u of t minus k is equal to, it is equal to 0 for t less than k, and it is equal to 1 for t greater than k. That means there is a value k, okay, and for values of t which is greater than, so you see this part, it means all the values of t which is greater than k. For these values, for these values of t, the value of this Heaviside step function is 1, and for all the values of t which is less than k, the value is going to be 0. Okay, so we have either 0 or 1. So this is a unit step function. Now this Heaviside unit step function is actually very useful because it allows us to represent very easily, it allows us to represent stepwise discontinuous functions, such as if I have a square pulse in signal processing. If you have a square pulse, then you can represent the square pulse very easily using Heaviside unit step function. So let's say I have a square pulse which is given as this. Okay, so we have f of t, which is it's a function of time. The value of this function, it is equal to a from 0 to t naught. Let's say from time t equal to 0 to time t equal to t naught. Let's say the function, it takes the value a. Then for t less than 0, it will take the value 0, and for t greater than t naught, it will take the value 0. So it is going to be non-zero only within this small window. Okay, between 0 and t naught, within this small window, it is going to be non-zero. Okay, and it will be 0 everywhere. So that's why it is a square pulse. So if I have a square pulse like this, now you can see here, this square pulse can be written, this function can be written very easily as a sum of two Heaviside unit step functions. Okay, remember, Heaviside step function, it is just a step, it just looks like a step like this. So I can use two Heaviside step functions to represent a unit to represent a square pulse. So consider these two cases. Okay, so let me reduce the size a little bit. Okay, so consider these two step functions. So this is also a unit step function, this is also a unit step function. Okay, so what is this unit step function? We can write this unit step function as u of t, because you see, Heaviside step function, it is u of t minus k. So if I make k equal to 0, that means this step, okay, this discontinuity that we have here, that discontinuity will occur at t equal to 0. Okay, so that's why we have this. So it is equal to simply u of t. So if I multiply this u of t with a, what will happen? Then here it takes only two values, 0 or 1. So if I multiply this function with a, what will happen is this will still remain 0 because 0 times a is 0, but this is going to become 1. Okay, so a into u of t is going to give us two values, either instead of Heaviside step function, it gives you either 0 or 1, but a into u of t is going to give us either 0 or is going to give us a. Okay, so this is a constant multiplied with a unit Heaviside step function, which in which the step occurs at t equals, it occurs at k equals 0. Now what about this function? So now you can see here, this is actually the Heaviside step function is supposed to look like this. It starts here and then it should increase like this. But if I multiply this Heaviside step function with a minus sign, then what will happen is it will just become the mirror image with respect to the x-axis, about the horizontal axis, will become a mirror image. So we have this minus sign over here, and then if we had a Heaviside unit step function like this, that would have been u of t minus t naught, because the transition is occurring at t naught. So it is u of t minus t naught, and then I multiply with minus a. So the moment I multiply with minus a, it is just going to become it's just going to flip with respect to the horizontal axis. So now if I add these two functions, if I add them together, you can see for yourself, here we have a 0, here also we have a 0. So 0 plus 0 will give us 0 in this region. Okay, in this region, so here I have here the value is a, okay, and here the value is 0. So a plus 0 is going to give us a. Okay, in this region we have a here. Okay, we have an a here, and here we have a minus a. Okay, so this a plus a and minus a will cancel out and we'll again get 0. So you can see here that if I just add these two functions, when I add them together, I'll get the unit square pulse. Okay, So this first function is this and the second function is this. So if I just add these two functions, that means the square pulse that we have here, that square pulse can be written as a sum of two Heaviside step functions. So f of t is equal to a ut minus ut minus t naught. Okay. So that's one of the utilities of the Heaviside unit step function. So now let's try to find out the Laplace transform of the Heaviside step function. So we have a Heaviside step function here in which the step occurs at t equals to k. So I want to find out the Laplace transform. So what I do is I just use the definition of the Laplace transform. All I need to do is in the integration e to the power minus st dt, I have to just replace the function f of t with u of t minus k. So this is what I did over here. Now in this unit step function, here originally the integration is from 0 to infinity. Okay, the integration is from 0 to infinity, but we know that from 0 to k it is going to be 0. We know that it is going to be 0 within this range of values. So we need not actually start our integration from 0. We might as well, instead of starting the integration from 0, we know that till here it's going to be 0. Instead of starting the integration from 0, we start the integration from k. So we change the limits, the lower limit, so instead of 0 we make it k. It is not going to affect at all. And then beyond k, what happens? What is the value of the unit step function? The beyond k, for all values of t, the value of the unit step function is 1. So I just replace this with 1 here. So it is simply an integration of an exponential function, which is the easiest thing to do. So e to the power minus st, integrate that from k to infinity, and then you integrate this. This is the result of this integration. Substituting the limits, you will get 1 by s e to the power minus sk. So this is the Laplace transform of the Heaviside unit step function. Okay, this is the Laplace transform. Now once we know the Laplace transform of the Heaviside unit step function, we can actually find out the Laplace transform of the square pulse also, because we know that the square pulse can be written as a sum of two Heaviside unit step function, and we know already what is the Laplace transform of a Heaviside step function. So what will be the Laplace transform of the square pulse? So that this square pulse, I want to find out the Laplace transform. I just replace the square pulse f of t with a u of t minus t naught. I replace that. Then using the distributive property, so if we have here, we can take the a, because a is a constant, so a comes outside. A times Laplace transform of u of t minus, because there is a minus sign over here, minus again a times Laplace transform of this function itself. Okay, so now this is easy because we already know what is the Laplace transform of the Heaviside step function. So here we have u of t implies that k is 0. K is 0 means, so we'll get a 0 over here. So 1 by s e to the power 0. So that's why we get a 1 by s e to the power 0. And the result of this one will be simply 1 by s e to the power, instead of k we have to replace this with t naught. So 1 by s e to the power minus s t naught. So the Laplace transform of this square pulse, this square pulse, it is a by s 1 minus e to the power minus s t naught. So that's the Laplace transform of a square pulse. So now you may be wondering, why do we need to find out the Laplace transform of the square pulse? You see, some problems are there in which, let's say I want to find out the derivative of a square pulse. So that becomes difficult. You can't, it's difficult to find out the derivative of such discontinuous functions. But you can always find out an expression for the derivative in the Laplace transform space, because we already have properties for finding the derivative, right? So we can which deal with the derivative. So we can convert that into a Laplace transform, find the derivative in the transform space, take the inverse transform. That will give us an expression for the derivative of the unit square pulse. Okay, so this is an application. Another application is, let's say I want to find out the inverse Laplace transform of this function. Okay, so I can use the partial method of partial fractions, which you are already familiar with. You had done this in your in the module on complex analysis. So this function that is given over here, remember this is a function of s. So we are trying to find out the inverse transform of this one. So let us assume that this function can be written as the sum of two fractions. So first fraction is, okay, we have in two terms in the two factors in the denominator. So we take one of the factors, which is s, so a by s, and the other factor, which is s square plus k square. So we have b by s square plus k square. Now we add these two together, and then in the numerator we have as square plus ak square plus bs divided by s into s square plus k square. So on the left hand side we already have this. Okay, so now if you compare the numerators on both sides, so we have k square here and we have a k square here. So if I compare this a k square with this one, so which means there is a 1 here, that means a must be equal to 1, so a is equal to 1. Okay, and secondly there is nothing else here, so that means this entire thing it must be equal to 0. So it means as square plus bs must be equal to 0, which means because a is already equal to 1, so we substitute 1 here, which means it's going to give us b is equal to minus s. So substituting these, so we have, say, a equal to 1 here and b equal to minus s, so that gives us f of s equal to 1 by s minus s by s square plus k square. Now finding the inverse Laplace transform of this, because we are trying to find out the inverse Laplace transform, so inverse Laplace transform of this is equal to the inverse Laplace transform of 1 by s minus the inverse Laplace transform of this. This is easy because we already have in the, from the table, we can just refer to the table here. So I want to find out the Laplace transform, inverse Laplace transform of 1 by s. So just search for 1 by s. Yes, here we have 1 by s over here. You take the inverse Laplace transform, you will get 1 here. So this answer is going to be here. We will have, so this result is going to be equal to 1. Okay, and minus again over here we look for s by s square plus k square. So s divided by here, s divided by s square plus k square. The inverse Laplace transform is cos kt minus cos kt. Okay, so that's the answer that we're looking for. So that's another application of the Laplace transform. Now, one more interesting application is, let's say, it also, Laplace transforms also allow us to evaluate integrals. So let's say I want to evaluate this integral. Okay, so you know that evaluation or again of this integral, it's a sine function divided by x, right? Divided by the variable itself. So we want to integrate this. This is not so straightforward. It's not so easy normally if you use calculus, but using Laplace transform it becomes easier. How does it become easier? You see, I say, let's say this is the function f of t. I want to find out the Laplace transform of the function itself, f of t. That means I want to find out the Laplace transform of the integral. Okay, so when I want to find out the Laplace transform of the integral, here I just use the definition of the Laplace transform. That is, the definition of the Laplace transform is you have to integrate e to the power minus st, and then whatever is the function, you just place the function as it is and then you integrate. So here it becomes a double integral. So we have an integral with respect to t and we have an integration with respect to x. Okay, so now I'm going to here first we are if you look at this expression, first we are supposed to integrate with respect to x, then with respect to t, but I'm going to swap the order of integration, so which I'm allowed to do because t and x, they are independent of each other. So first I'm going to integrate with respect to t and then I'm going to integrate with respect to x. So integration with respect to t, that means this 1 by x, it can come outside, this integration with respect to t. So 1 by x outside, so integration e to the power minus st sine tx dt. Okay, and then this one we immediately see that this is nothing but we are trying to find out the Laplace transform of sine tx. Okay, so this is nothing but the Laplace transform of sine tx. We already know the Laplace transform of sine tx from the table of transforms. The Laplace transform of sine, wait a minute, here, sine tx, t is the variable, x, instead of x we'll have k. Okay, that's what we are going to do here. So here tx, we wrote it as sine kt. Okay, t is the same over here, t is the same over here. Only thing is, instead of, we'll replace here wherever it is k, we'll replace it with x. So we know the Laplace transform, this is k by s square plus k square. So we replace this k with x here and this k also with x here. So we'll get x divided by s square plus x square. Okay, so this is going to give us x divided by s square plus x square. So now we see that this x and this x will get cancelled out, and then as a result we'll get integration dx by s square plus x square. Now this integration is it's a standard integral. It is nothing but the integral 1 by s. The result of this integral will give you the tan inverse function. So tan inverse of s by x by s. So we take the limits from 0 to infinity, and then 1 by s, you put the limits tan inverse at infinity minus tan inverse at 0. Tan inverse, the tan function takes the value infinity at pi by 2, and the tan function takes the value 0 at the angle 0. So as a result, we'll get, the Laplace transform of this integral will become equal to pi by s. This is a very simple result that we got. Now if I want to find out the integral itself, so what do I have to do? I have to take the inverse Laplace transform. So the value of the integral will be the inverse Laplace transform of pi by twice s. So pi by 2 is anyway a constant, so it will come outside. So we end up taking the Laplace transform of 1 by s. So Laplace transform of 1 by s, and we know that the Laplace transform of 1 by s is equal to 1, because that was the very first elementary result that we did. Laplace transform of 1 by s is simply equal to 1. So this is going to give us 1. So as a result, the value of this integral will be pi by 2. But what about the condition? The condition is t has to be positive. Okay, t has to be positive. Okay, so now let's look at the case where t is not positive. So in that case, what happens? So if in this function, if I replace t with minus t, then here wherever there is t, I have to replace t with minus t. So here we'll have a minus sine of minus tx. Now sine minus theta is equal to minus sine theta. So as a result, this minus will come outside. So minus sine tx by x into dx. So which means this is an odd function. So f of minus t is equal to minus f of t. And at t equal to 0, f of 0 will be equal to 0. Then the complete integral will be, I'm trying to find out the integral for all values of t. For positive values of t, it will take the value of pi by 2, which we have already found out over here for positive values of t. For negative values of t, it will be minus pi by 2. This is from the fact that the sine is an odd function. And for t equal to 0, it will take the value 0. So you could plot this integral with respect as a function of t. The value of the integral itself as a function of t. So it is going to be a step function like this. Okay, so it will be a step function like this. Now the moment there is a step discontinuity like this, we immediately, what comes to our mind is the Heaviside step function. Okay, so I'll leave it to you to verify that this function can be written as in terms of the Heaviside step function like this. Okay, I'll give you a hint. It is in the same way as we wrote the square pulse, like here, how we are able to write down the square pulse as the sum of two Heaviside step function. So in a similar way here, this entire function which you are writing in terms of discontinuities like this, you can express it in terms of Heaviside step function. So I'll leave it to you to verify this for yourself. Okay, so now let's take a physical example. So we'll take two examples. One is for, of course, the simple harmonic oscillator. Another one is the damped oscillator. So what happens in a case of a simple harmonic oscillator is, from the ceiling we have a spring of spring constant k, and there is a mass m which is suspended, and then this we allow this mass to perform oscillations with respect to its mean position. So this dotted line, this is the mean position, and this is the displacement with respect to the mean position. So here we are neglecting friction and air resistance, that this is the undamped case. That's why we are having simple harmonic oscillator, and the oscillations are small. Then x is the instantaneous displacement of mass. So the equation of motion, you all already know how to do this. From Newton's second law, we have net force is equal to mass times acceleration. The net force, there is only one force, which is the spring force, which is minus kx. What about gravity? Gravity gets balanced out, and when it is at its equilibrium position, it gets balanced out. So we don't include gravity over here. So we have minus kx, that's the net force. So it is moving only under the influence of the spring force. So minus kx, which is equal to m, and acceleration is nothing but the second derivative of position. So we write this as d square x by dt square. We take this and bring it onto the other side. Okay, so we have this minus is going to become plus. So m into d square x by dt square plus kx is equal to 0. Now what about the initial condition? The initial conditions, let's say we'll assume that at t equal to 0, the mass was at rest. If it is at it was at rest, and it was at one of the extreme positions. Okay, so let's say the extreme position is x0. So the initial position at t equal to 0, it is x0, and because it was at rest, the first derivative of position is velocity, so x dot is velocity, so x dot at t equal to 0, it will be 0 because it's at rest. So now we take the Laplace transform of equation number 1. So when you take the Laplace transform equation number 1, so you are taking m times Laplace transform of d square x by dt square plus k times Laplace transform of x. So let's call this equation number 2. So now we already know how this works whenever you have derivative. We saw that in the previous class. Sorry, it's over here. The derivative, transforms of derivative. Yeah, we use this formula. For second derivative, we already have obtained this case, the expression. This was the expression for the second derivative. In case of second derivative, the Laplace transform of the second derivative of the function is equal to s square, the Laplace transform of the function minus s f0 minus f prime 0. Okay, so we just use this formula here. So Laplace transform of the second derivative will be, first we have s square, so s square, Laplace transform of f of t, here f of t is nothing but x of t, minus s, which is here, times f of 0, here which is f is nothing but x of 0, minus f prime 0, I am writing it as x dot because we are differentiating with respect to time. We know that this is differentiation with respect to time, but here t is time. So now from the initial conditions, what do we have? We have x of 0 is x naught and x dot of 0 is 0. So which means this is going to be 0. Okay, this is going to be equal to 0 and this will be equal to x naught. Okay, so as a result, we will get the Laplace transform of the second derivative is equal to s square, the Laplace transform of the position minus s x naught. So substituting this in equation number 2, okay, just take this expression, okay, and then just replace it over here. So this is what gives us, so m, so we have m times s square into Laplace transform of x minus m times s x naught, and then here we have kl x of t. Okay, here let us say x of the Laplace transform of capital X. Okay, this is the position. This one's Laplace transform. Let's call it as small x of s. Okay, just want to make things look a little bit easier to easier to comprehend. So the Laplace transform of capital X, I'm just writing it as small x of x, x of s. And here again similarly, Laplace transform of capital X, small x of s. Okay, so this is what we have. So small x of s is nothing but the Laplace transform of capital X. So I can take here we have a x of s and here also we have a x of s. I could take this as common and then we'll have ms square plus k. So ms square plus k x of s minus ms x naught, which is equal to 0. So from here we have x of s is equal to ms x naught by ms square plus k. So now I could take this m common from the denominator. If I take m common, because this m and this m will get cancelled then. So we have s square, that means this k has to be divided by m, so k by m. Okay, so I take this x naught just so that it looks a little better. So x naught, and then we have s divided by s plus k by m. So this k by m, just replace it with omega square. You already know that this is nothing but the angular frequency. So s divided by s square plus omega square. Then from equation number 3, that is this equation, we know that x of s is the Laplace transform of this. So x of s is the Laplace transform of x of t. That means x of t is the inverse Laplace transform of x of s. So I want to find out x of t. Remember, we are interested in position as a function of time. We are not interested in x of s. It is just a tool which is going to help us find out x of t. Remember that. Okay, so x of t is equal to inverse Laplace transform of x of s. So x of s we found out it is equal to x naught s by s square plus omega square. So I can take this x naught outside because of the linearity property, and then Laplace transform of s by s square plus omega square. So we already know again from our table of transforms. From the table of transforms, we just have to look for an expression which looks like this: s divided by s square plus some constant. So let's look for this s. Here it is. So s divided by s square plus some constant. K is a constant here. Just it happens that this k is instead of k, okay, this k we just replace it with omega. Okay. So here, what is the inverse Laplace transform? It is simply cos kt. So remember, k is replaced with omega. So here also we have to replace k with omega. So this gives us x of t is equal to x naught cos omega t, which you all are already familiar. This is nothing but the simple harmonic oscillator, the expression for the solution of a simple harmonic oscillator. It's a sinusoidal function. Because it starts from one of the extreme positions. The initial condition says that it starts from one of the extreme positions, so we expect it to have a cosine variation, not a sine variation. Okay, so that's about the simple harmonic oscillator. Now let's have a look at the damped oscillator. Damped oscillator is similar to a simple harmonic oscillator, except that now we are allowing the mass, we are immersing the mass inside, let's say, some fluid, and this fluid has got some damping constant. Okay, so in this case, what will happen? Again, from Newton's second law, the net force is equal to m times a. But here there will be an additional force. That force will come from the damping, and we know that the damping force is always opposite to the velocity. So it'll have a minus sign, minus the damping constant times the velocity. So earlier it was only for simple harmonic motion, only there was x and x double dot. Now we have x dot as well as x double dot. So I just bring everything to one side, and then we have m d square x by dt squared plus b dx by dt plus kx is equal to 0. Let's call this equation number 1. Suppose at t equal to 0, the mass was at rest at its extreme position, just the same as before. The initial conditions are just the same as earlier. Then we take the Laplace transform of this equation. So when take the Laplace transform, so we have m times the Laplace transform of the second derivative of x plus b times the Laplace transform of the first derivative of x plus k times the Laplace transform of x itself is equal to 0. So we can evaluate this in a similar way using that derivative of transform of derivative. We can use that formula. Okay, I'll leave it to you to work this out. This is of course exactly the same as what we had done for simple harmonic motion. This one I leave it to you to verify that this is indeed going to be the case. So we need to just replace this over here and this over here, and making this replacement we get this expression. Okay, so now here I take x of s. Again, what is x of s? As before, it is the Laplace transform of capital X of t. So I take x of s common, so we have an x of s here, x of s here, and x of s here. So we'll get three terms: ms square from here, and bs from here, and k from here times x of s. And then whatever is left, there is an x naught term here, another x naught term here. Both of them are negative. They go to the other side, they will become positive. So we have ms from here and b from here times x naught. So this gives us x of s is equal to ms plus b x naught divided by this entire thing, which goes into the denominator on the right hand side. Now I take, as before, I take the m common. So in the numerator we have s, and then this b by m, we'll get a b by m. So here we'll get again divided by m, so we have an s square. Here again we have, because we have to divide by m, so we have b by m. Then we have k by m. Okay, call this equation number 3. Now we'll need to complete the square of the denominator over here. So to do that, what we do is we do it this way. We write this expression, the entire expression in the denominator, we write it in this way. So I'll leave it to you again to verify that if you if you expand this and cancel out the terms, you'll get the same thing as before. Okay, very straightforward. Now we are considering the case of underdamping. Okay, underdamping. What is underdamping? Underdamping is when the damping constant is less than 4 mK. Okay, so there are, if you remember from your classical mechanics, there are 4 cases of damping. One is the undamped case, in which b is 0. Then another case is the underdamping, in which b square is less than 4 mK. Then we have critical damping, where b is equal to 4 mK, and then we have overdamping, where b square is 4 mK. So we are considering the underdamping case, where the oscillations, they will just die down. So that's the underdamping case. So for that, the condition is b square must be less than 4 mK. So it means b square by 4m is less than k, which means if I divide this by m, so we have there will be a m square here. So b square by 4m square. Here there will be a m in the denominator, k by m. So that means k by m is greater than b square by 4m. That means k by m minus b square by 4m, this will be always positive. So this quantity that you see here, this is a quantity which will always be a positive quantity. So if it is always positive, we can go ahead and we can define it as some kind of a square of an angular frequency. After all, k by m will give you m naught, omega naught. In the case of simple harmonic motion, k by m has got dimensions of square of angular frequency, which means, and we are adding these two terms, that means this will also have the dimensions of omega square, the square of angular frequency. So together this quantity will have dimensions of angular frequency. So this angular frequency, I'll call it as omega 1 square. So the denominator that we have, okay, this denominator in equation number 3, this denominator can be simply written as s plus b by twice m whole square plus omega 1 square. Then equation number 3, it simply becomes like this. Now this b by m, I split this, I write this as b by twice m and b by twice m, okay, and then I open up the fractions. So here first I'll take s plus b by twice m as one fraction, and then b by twice m divided by this I take as another fraction. Then this b by twice m I multiply and divide by omega 1, okay, I do that. And then we have x of s is equal to, I take this x naught, I take it common, and this entire thing, okay, this is one term, and then here also I take x naught common, and this b by twice m omega 1, this also I bring it outside, okay, along with this x naught, because all of them are constants. So b x naught by twice m omega 1. So this leaves behind an omega 1 here. So omega 1 divided by b by s plus b by twice m square plus omega 1 square. Let's call this equation number 4. Then we use these results from our table of transforms. From this table of transforms, e to the power at sine kt, we saw this in one of the properties earlier also. We could derive this from the Laplace transform of sine kt and cos kt. So e to the power at sine kt, the Laplace transform is this, or the Laplace transform of this one is this, and the Laplace transform of this is this. So which is with what we have written over here. So these are the two results that we'll be using. So here in these expressions, if I because there is a here, if I say a is equal to minus b by twice m, okay, let's put some values here. A is equal to minus b by twice m, and this k, if I make it equal to omega 1, then what will happen? Let's first take this expression. Okay, let's first take this expression. So we have e to the power, there is a here, a I'm replacing it with minus b by twice m, so e to the power minus bt by twice m, and then cos k I'm writing it as omega 1, so cos of omega 1 t. What will this be equal to? It will be equal to s minus a, again a is equal to b by twice m minus b by twice m, that minus and this minus will give us a plus sign here, and here s plus, because a b by twice m, s plus b by twice m whole square plus k, I replace it with omega 1. So which means if I take the inverse Laplace transform of this, it will give me this quantity inside the which is whose Laplace transform I found out. So Laplace transform of this is equal to this, which means inverse Laplace transform of this is equal to this quantity. Okay. Similar way, for using this expression, we find out that the inverse Laplace transform of this quantity is equal to simply this. Then if we take the inverse Laplace transform of equation number 4, inverse Laplace transform, this on the left hand side, it is going to give us simply x of t, that times x of t is equal to x naught times the inverse Laplace transform of this plus this into x inverse Laplace transform of this. So x naught into inverse Laplace transform of this, and then so on. We have shown that the inverse Laplace transform, the inverse Laplace transform of this is equal to this. Okay, so that's why we replace this with e to the power minus bt by twice m cos omega 1 t, and then here we have this quantity already, which is a constant. The inverse Laplace transform of this is equal to e to the power minus bt by twice m sin omega 1 t. So I can take e to the x naught e to the power minus bt by twice m, I can take it common. So what we have left here is cos omega 1 t plus b by twice m omega 1 sin omega 1 t. Call this equation number 5. Rest what we have is some algebraic and trigonometric manipulations. We define an angle, a phase angle phi, to be b by twice m omega 1, and the phase angle phi to be equal to a tan inverse of b by twice m omega 1, which means tan phi is equal to b by twice m omega 1. So and over here in this quantity inside the bracket, we'll try to simplify this now. So cos omega 1 plus b by twice m omega 1 sin omega t, this we have redefined as tan phi. So we replace this with tan phi. Tan phi is nothing but sin phi by cos phi. Then you multiply this cos phi with this one. We have cos omega 1 t cos phi plus sin omega 1 t sin phi. And this cos phi, I could write this as, because it's 1 by cos phi, I could write this as secant phi. And this one is nothing but cos A minus B, trigonometric identity. So it is, we can simply write it as cos of omega 1 t minus phi. Now a secant square, we use this trigonometric relation, secant square is 1 plus tan square phi. So 1 plus tan square, tan phi is this one. So we just take the square of that, we get this. Now you just add these two, so we this goes up, so we have 4m square omega 1 square plus b square. Here if I take this from here, okay, if I take we have just a minute, yeah, here we have omega 1. I just replace the definition of omega. What is omega? We defined omega in this way, omega 1, sorry. Here we defined omega 1 in this way, so omega 1 square in this way. So we just substitute that definition of omega 1 square, because it's omega 1 square. I substituted that definition, and then what we have here is 4m square by km. We have this one, then this 4m square and this 4m square will get cancelled, we'll get minus b square. Consequently, this minus b square and this plus b square will cancel out. Once they cancel out, this 4m square and this 4m square will also cancel out. So what we have here is k by m by omega 1 square. This k by m is nothing but omega naught square, which we had defined for a simple harmonic case. So omega naught by omega 1. Okay, and what was there on the left hand side? Left hand side we have secant square phi, which means secant phi is simply this ratio, omega naught by omega 1. So as a result, in this equation here, this entire thing is nothing but secant phi cos omega 1 t minus phi, and secant phi is simply omega naught by omega 1. So as a result, that equation number 5, it will simply become x naught omega naught by omega 1. This comes from that secant phi e to the power minus bt by twice m cos of omega 1 t minus phi. And if you plot this, you will get that familiar, that underdamped case. Okay, so where all these terms, they are mentioned over here. So this represents the motion of a damped oscillator. Now coming to the last topic, which is a Laplace convolution theorem. So here the idea is that of a convolution. So I'll not be doing much in details. I'll just tell you what a convolution of function is and how the Laplace transforms is actually the Laplace convolution theorem. It actually makes calculation of this convolution. It makes it very simple. Okay, so what is the convolution? So suppose I have two functions, f1 and f2. Then the convolution between these two functions, it's an integral operation, and it is defined in this way. We generally write it like this. Okay, so we write it as f1 star f2. This is defined as integration from 0 to t, f1 where it is shifted by an amount, okay, t minus z, f2 z, and then we integrate with respect to z. Okay, so essentially we are doing a mirroring of one of the functions and translate and then superimpose both of these and take the integral. So it basically is we are trying to find out the overlap integral between these two functions. Okay, so this convolution is very common in signal processing, and it is it's a commutative it's a commutative operation. That is, it really does not matter in which order you do the convolution, whether it's f1 star f2 or f2 star f1, doesn't matter. So now this may not make much sense to you, so to help you understand, there is a demo which I have over here, a convolution demo. So let me show you the demo here. You can just click on this and it is going to show you. There is this page where this demonstration is done, so just to help you understand what this convolution process is. So when you click on, if you click on this one, it will take you to this page. So this is a definition of convolution. So here we have two functions. I'll show you what this convolution means. So let's say we have two functions. Okay, these are the two functions. This red is one function and this blue is another function. So we want to find out the convolution. You can see the blue one is a Heaviside step function. So red function, it is just some kind of a pulse. So we want to find out what is the convolution between of these two functions. So to do that, what we have to do is I'll just show you how it works. Okay, so what we have to do is we have to take a mirror image of one of the functions and then just move it, keep the other function fixed. So here the heaviside step function is kept fixed, and this red color, this pulse function, you take a mirror image of that. You just watch this one. Okay, the second diagram, you can see here, this is the same red function, but you're taking a mirror image of that. Okay, and this blue function, it remains fixed. Okay, so what we are trying to do is we are trying to take the product of this red function, take the product of this one with this one, and then we integrate that product. Okay, so that is going to be given by this purple line, and the result, that will be the area under that integral, that will be given by this green line. You can see what happens. Just observe what happens to that black dot. So let's say I start moving it. Okay, I'll start moving it towards the right side, keep moving it towards the right side. You see there is no overlap between the two functions. Because there is no overlap between the two functions, you can see there is no the two functions, they are not overlapping with each other. So therefore the overlap integral value will be 0. You can see here the value is 0. So you bring this some more. So now this is the place here. This is where they just start overlapping. You can see here they just start overlapping. Now if I bring this function, the red function, if I bring it some more, you can see that there is some kind of an overlap, right? This purple part, this is the overlap integral. So you take the area of this purple, you take the area. That area, you see, it has now increased. Now bring this some more. The overlap is increasing even more. You can see here, this value is also increasing. Okay, the overlap integral value. You bring it some more, it increases, Eventually, finally what will happen is the entire function will overlap. Okay, so there is an overlap between the entire function. Now because it's a heaviside step function, so it is not going to change. So now as this the red function, as it proceeds, the overlap area, it does not change. The overlap area remains constant, and as a result we will have, this is a convolution result. Okay, this will also remain constant. Okay, once again, here the two functions, they are not overlapping, so the convolution is 0. It's going to be 0. It's going to remain 0 until and unless there is no overlap. Now the moment they start overlapping, the green one, the third graph, you see it will also start increasing. That means the convolution is going to increase. It increases and it continues like this. Okay, so that's a demonstration of what exactly the convolution is. Okay, now it looks like a very difficult process to handle, and in fact it is, because it's an integral of two functions. But then the Laplace, there's something called as the Laplace convolution theorem, which actually makes it easy. It's known as the Fulton theorem. It makes it really easy. So the statement of that is the Laplace transform of the convolution of two functions is equal to the product of their Laplace transforms. Okay, so suppose I have two functions f1 and f2, and their respective Laplace transforms are this. So f1s is the Laplace transform of f1t, f2s is the Laplace transform of f2t. Then I want to find out the Laplace transform of the convolution between them. All I need to do is just take the individual Laplace transform and just multiply them together. That's all. And then if I want to find out, then from there I can find out the convolution very easily. All I need to do is just take the inverse Laplace transform of the product of these two. Okay, so a very simple example is let us say I want to prove this result, that is the Laplace transform of this integral is equal to 1 by s f of s. What is f of s? F of s is the Laplace transform of this function. So we say that f of s here is the Laplace transform of this given function. So let's say I define two functions, f1 is 1, is just a constant function, and f2 is this function f of s. Okay, so this integral that we are trying to find out, integration from 0 to t fx dx, it is nothing but integration from 0 to t, which is nothing but 1 into f of x, and this 1 I could just write it as f1 t minus x, doesn't matter because f1 is anyway a constant function, and then this f of x I could just write it as f2. Okay, so we have this what we see over here, this is nothing but the convolution. Okay, it's nothing but the convolution operation as we saw over here. Okay, this is nothing but the convolution operation. So we can just write down on the right hand side, we can just write it as convolution of f1 and f2. So by the Laplace convolution theorem, we are trying to find out the Laplace transform of this. So the Laplace transform of this integral is equal to the Laplace transform of the convolution of the two functions. So by the Laplace convolution theorem, it must be equal to the product of the two Laplace transforms. So the first Laplace transform, the first function is 1 and the second function is f of t. Laplace transform of 1 is 1 by s, so this proves the result. This is the simple example of the Laplace convolution theorem. So with this I come to the end of this lecture. Thank you.